a kingdom of scientific research, a new domain of man's own creation, a world of primary substances which never existed before. The aristocrats of this new realm are the phenolic plastics, of which Bakelite resinoids are the first family.
Wherever you turn today, there's pretty sure to be a modern plastic in use somewhere within sight.
Yes, that's why my editor wants a story on the industry and its background.
Well, of course, natural plastic materials are as old as recorded history. But the so-called modern plastic first became a factor in industry in 1907. That's the year that Dr. L.H. Bakelite announced his invention of an entirely new synthetic substance, phenolic plastics. They were the first in industrial importance.
How would you class his invention? Accidental or premeditated?
There's your answer. Those are Dr. Bakeland's original laboratory notes and records of tests. 8 years of them.
This begins to look like a tough assignment.
Plastics, that is, the so-called modern ones, are more complicated than metals. But now that we know their secret, they're easily explained.
Remember, I'm only a reporter. And what's more, I had an awful time passing high school chemistry.
I tell you what we'll do. We'll use Dr. Bakeland's original formula for our demonstration. Now, he started with two main raw materials: phenol, commonly known as carbolic acid, and formaldehyde.
Aren't they the chemicals used for disinfectants?
That's right. For the first part of the process, all we need is this burner, this flask, and this reflux condenser.
Just a moment, please. What's the reflux condenser for?
Well, that merely returns the condensed vapors to the flask. Now, the flask already contains the proper amount of phenol. Now we pour in the other principal ingredient. This is a solution of formaldehyde in water, commonly known as formalin. It so happens that these two chemicals have a natural tendency to react upon each other and combine. But to further aid this reaction, Dr. Bakeland added a catalyst, or chemical agent, such as this. The solution is now ready for the next step, heating. By magnifying the molecules of phenol and formaldehyde a few million diameters, we can observe what happens as the reaction proceeds. Because these starting molecules are different, this is called a condensation process. The water resulting from the condensation is removed by replacing the reflux condenser with one of ordinary type. Now, under the action of continued heat, the water is evaporated off into this other container. Now, the resin-like substance left in the flask, Dr. Bakeland called phenolic resinoid A, or his primary product.
What's the meaning of the word resinoid?
Oh, it was coined by Dr. Bakeland to distinguish his new synthetic materials from natural resins.
By the way, is that where the trade name Bakelite came from? Dr. Bakeland, the inventor?
Correct.
May I ask why the resinoid is called a primary product at this stage?
In the A stage, it can be melted and thinned or hardened and pulverized. This is the point where it's adapted to different kinds of fabrication, like molding and casting, for example.
If possible, I'd like to see one of those operations.
Well, casting is simplest because it's done directly from the primary resinoid. So I'll cast a small rod to show you what occurs in the final stage of Dr. Bakeland's process. In this closed chamber, the liquid resinoid in the tube can be heated under controlled conditions. This factor of control is all important. Unlike the molecules at the start of the first stage, these, you will notice, are all the same. Now keep a sharp eye on them. Several of the smaller ones are combining to form larger molecules. The result is a material of the same chemical composition, but with entirely different physical properties. This process chemists call polymerization. By means of it, phenolic resinoid changes from the fusible and finally turns, or freezes, into resinoid C. It's now a hard, insoluble, and infusible solid, which takes the exact form of the mold, in this case a test tube. And here's our cast rod, an exact duplicate of the one first cast by Dr. Bakelite in his own laboratory back in 1907.
It's like a fine piece of amber. Are all the materials that you now produce made from the original formula?
No, indeed. Hundreds of new formulas have been developed since the original invention. Many new raw materials and processes have been introduced, resulting in over 2,000 different types of Bakelite materials.
To grow to that number, they must have played an important part in the progress of industry since 1907.
Oh, to take volumes to tell that story. For example, they made possible the foolproof ignition system of the automobile. They've expanded to 1,000 uses and places in our communication systems, telephone, telegraph, and radio. They grew up with the aviation industry. But the list is endless. Perhaps the best way to illustrate their importance to industry today is to take you to Bound Brook, where Bakelite materials are made on a commercial scale.
Out of the discoveries and patents of Dr. L.H. Bakelite has grown a world-circling empire of plastics. And here is its capital, Bound Brook, New Jersey. Every building and room of this modern 125-acre plant was designed for but one purpose, the manufacture of Bakelite materials. Its production equipment is the perfected development of a quarter-century's experience in making plastics. From many raw materials are now manufactured an infinite variety of primary resinoids covering a wide range of special characteristics and properties. These, alone or in combination with numerous fillers and solvents, make up the more than 2,000 different Bakelite materials. They are supplied to the trade, ready for use, in manifold forms suited to fabrication and quantity production. Molding materials, for example, are prepared as powders, molding flakes, board stock, and blanks. But regardless of form or application, all Bakelite materials, by virtue of their primary ingredient, the resinoid, possess in common a unique combination of superior properties. Exceptional in their tensile and impact strength, hardness, durability, and electrical characteristics, they have in addition high resistance to heat, water, and chemicals. Any of these qualities, furthermore, may be augmented by varying the type and amount of the modifying agent. Molding powder pouring into these telephone shell molds is prepared by combining resinoid with a cellulose filler. Fillers such as this and cotton fabric, asbestos and minerals are incorporated in molding materials for their added value. Better molding qualities, greater toughness and strength, and in the case of mineral fillers, an increased degree of water and heat resistance. But the resinoid is the important ingredient. And it's this combination of characteristics, rather than any one single property, which inspired the use of molding materials in so many different products. From another form of molding material, called molding blanks and board stock, are fabricated special products needing unusual strength by reason of their form or use. And like this molded funnel, all types of these materials have the structure and resiliency necessary to withstand turning, drilling, threading, buffing, or any of the operations employed in machining metal. Bakelite materials entered the automotive field in molded distributor heads when Charles F. Kettering developed his Delco ignition and starting system. In these new plastics, Mr. Kettering found the dielectric strength, the resistance to heat, acids, oil, and moisture, in fact, the very insulating material which he needed. Now there are over 200 resinoid parts in the modern car. Long before listeners had heard the term radio, molding materials were aiding the makers of radio's parent, wireless telegraphy. Today, they guard 1,001 vital spots in the great broadcasting stations and home receiving sets. In the electrical industry, the molding of instrument cases is typical of simplified production. Formerly involving 15 machining and finishing operations, they now are made with resinoids in a single closing of the press. Big or little, resinoid molding materials are equally adaptable, as witness these tiny insulator bushings and these two examples among many home electrical devices. Development of scores of materials for special uses has prompted the spread of molded applications into many diverse and new fields. Here, for instance, are products fabricated from a more heat-resistant material of the mineral-filled type. Another new variety, impact materials, has several times the shock resistance of ordinary molded plastics. This product consists of phenolic resinoid processed with specially selected fibrous fillers. Holding the spotlight in modern merchandising are packages and closures produced from molding materials. The unmistakable feel of quality, the sales appeal, and utility of these colored molded products have earned their approval by retailers and public alike. Then, too, the inert, chemical-resistant properties of the materials make possible sanitary leak-proof jar, tube, and bottle tops. These resist alcohol and are non-corrodable. Novelties likewise have joined the army of products whose appearance is enhanced through the use of these brilliant surfaced materials. Transparent materials are produced from pure resinoid without the use of fillers. They are cast in lead molds and converted into consumer products by machining. Rivaling precious jewels in color and depth, they are among the most beautiful of resinoid products. For the manufacturer, artist, designer, and amateur craftsman, they have opened up a new field of wide possibilities. And for the public, new means of decoration and service.
This jet necklace, madam, is Bakelite resinoid. We consider it equal if not better than the natural mineral.
It's beautiful. And how light. And so smooth and warm to the touch. But will it keep its fine appearance?
Yes, permanently. As a matter of fact, Bakelite jewelry has many advantages over glass, porcelain, and natural stones. To start with, it's flawless. Then, too, it is strong and hard without being fragile.
The material in this holder is so strong that a 7-passenger car can be hung on a 1-inch rod of it. An engineer told me that.
Well, then it can't be amber. That's quite brittle.
No, sir, it's called Bakelite RESINOID. Notice the smooth surface on this pipe stem. The material is dense, non-absorbent, and has an enduring finish. That's why it's not affected by mouth or tobacco acid.
Among their many strictly utilitarian uses, Bakelite transparent materials, by reason of their chemical resistant properties, supply graduates, bottles, and other laboratory apparatus which must withstand the destructive action of hydrofluoric acid, and thereby they meet a century-old demand of chemists. Laminated materials are products of the chemical merger of phenolic resinoids with layers of paper or fabric. Under controlled and recorded conditions, great rolls of laminating fabric are uniformly coated with resinoid in varnish form. Dried and then cut into sheets, the processed fabric is weighed and stacked between polished metal plates. This impregnated mass goes now into a hydraulic press wherein the miracle of polymerization takes place under heat. Soon it comes out a hard, dense, rigid plate which requires only trimming to size. But in any of its forms, sheets, tubes, or rods, laminated makes available to industry a material with high resistance to moisture, uniform wear, resistance to temperature and chemicals. Outstanding also are its ease of fabrication and remarkable insulation qualities, its freedom from fracture and structural variation, its high tensile and compressive strengths. Its applications are legion. Suited to mass production, all manner of articles are punched from it. In a host of parts on practically every make of radio set, Bakelite laminated has become the standard insulating material. Equally wide is its service in 100 critical places in central stations and throughout the electric power industry. It is the durable material of silent gears in industrial machinery and automobile timing trains. And from still another type of laminated stock are cut the breaker strips for the doors of automatic refrigerators. It may be had in a range of colored effects from lustrous jet black to robin's egg blue, combined, if desired, with tinted metal inlays and photomurals. It is the newest and most versatile medium of the modern designer and architect. Bakelite lacquers are made by dissolving primary resinoid in suitable solvents. Light amber in color, they are intended primarily as protective coating. To highly finished articles, they are applied by machine dipping or by spraying with standard airbrush equipment. The thin film of resinoid is then oven-baked into a brilliant and wear-proof coating. By reason of its high mechanical bonding strength, dielectric value, and resistance to oil, water, dirt, and gasoline, Bakelite varnish is widely used as an insulating bond and protective coating for coils, armatures, and windings. To automotive brake linings, it imparts long life and resistance to friction heat. It even protects museum fossils. Resinoid cement contains a solid reinforcing body in addition to the resinoid and solvents. One type, lamp basing cement, has long been used to seal electric lamps and radio tubes in their bases. Another, bristle setting cement, furnishes a solvent-resistant bond and makes possible the assembly of the bristles and handles in one operation. Can you imagine a mechanical device containing 75 million sharp cutting tools? Believe it or not, you are watching the manufacture of such an incredible industrial implement. It's a modern high-speed abrasive wheel, bonded with Bakelite resinoid. Without these faster cutting, safer, cooler running grinding wheels, it would be impossible to machine and use the present-day alloy steels. And only through high accuracy in quantity production, which grinding alone can achieve at low cost, is industry able to produce economically high-speed, high-powered machinery, tools, automobiles, and aircraft. The gluing together of sheets of wood or veneers, now called plywood, dates back 35 centuries to the Egyptian pharaohs. But until the introduction of resinoid bonds for the plywood industry, delamination and stains were a constant source of trouble in wet gluing. These resinoid adhesives knit the wood fibers securely together and form a synthetic wood, more uniformly durable and stronger than the original lumber. And heat, humidity, water, vermin, and fungi, none of these enemies of ordinary wet glued veneers can impair the lasting qualities of resinoid bonded plywoods. Behind this container of resinoid denture material stretched 20 years of research in the Bakelite laboratories. From the first operation, luxine technique is simple. Placed under heat, the resinoid becomes semifluid and enters into every crevice of the mold. And when the mold is later removed and opened, the denture is found cured into a hard, dense material, a permanent reproduction of the wax pattern. Then stripped of plaster and tin foil, it requires only finishing and polishing with the dentist's regular equipment. And combined in it are natural color, strength, luster, lack of odor and taste, hygienic advantages, and repairability. These are the properties that have induced over 1 million men and women to use a luxine denture. New possibilities in industry, decoration, and apparel are offered by Revolite, an amazingly versatile fabric treated with still another Bakelite product, flexible resinoid. In contrast to the surface-coated cloth on the market today, Revolite is processed so that the resinoid is forced into the fibers of the material, thereby becoming an integral part of the fabric. It is a waterproof cloth, resistant to chemicals, and can be washed with soap and water and safely ironed. Revolite is made in a wide range of colors and brilliant metallic finishes. Its beauty and utility, and its usability both indoors and out, make this modern material particularly desirable for the upholsterer, the manufacturer of household coverings, the interior and stage decorator, and the designer of woman's apparel. Synthetic resins for paints and varnishes are produced to meet the present demands for quicker drying and more durable finishes. The paint manufacturer's chemist, however, sees in these resins an opportunity to strengthen the desirable qualities in his company's products, to meet more completely the constant requests for special purpose paints and varnishes, even to open up whole new markets. New types of bridges, modern structures, and streamlined trains, utilizing new materials and design, have all presented difficult problems of surface protection. Surrounded as they are in seacoast regions and industrial centers by atmosphere laden with salt spray, corrosive acids, and alkalis, their upkeep has always been a costly matter. But durable protective coatings based on synthetic phenolic resins now pave the way for substantial economies in maintenance costs. Resistance to abrasion and washing compounds is another fundamental quality of synthetic resin finishes, which is bringing about their extended application on floors and automobile bodies, or on any surface subject to excessive wear. The industries must have the protection of chemically resistant varnishes and paints. Furniture and product finishes demand gloss, luster retention, and durability. Aircraft finishes need resistance to sun and sleet, fumes, and dirt. Yacht and marine craft finishes must withstand sun, rain, and salt spray. These are but few of the specifications of Bakelite resin paints and varnishes. Born in a chemist's test tube into the fourth kingdom of primary substances, resinoid plastics grew up and were made useful in these extensive research laboratories of the Bakelite Corporation. And here, too, they are multiplied and adapted to the future needs of every industry on Earth. Their limitless applications can be measured only by the sign for infinity, and that's the symbolic trademark of Bakelite products.